Good morning. I'm Jeff Hammond, Executive Director at International Ground Source Heat Pump Association. Welcome to our May IGSPA Dig Deeper webinar. Got to wake up this morning. I'm happy to say that this Dig Deeper webinar is sponsored by Climate Control Group. Those companies are Climate Master Geothermal Heat Pumps, International Environmental Fan Coils, and Climate Cool Modular Chillers. And we thank Climate Control Group for sponsoring this Dig Deeper. Before we get started, I have just a few updates so that you can be up to date on the latest IGSPA news, and then I'll turn it over to our speaker. So the latest IGSPA news is certainly regarding this Dig Deeper. We have all of our Dig Deeper and Town Hall webinars filled for the rest of 2023. So thank you very much for the speakers who have agreed to do these webinars. You can still submit a form. If you go to the IGSPA website, igspa.org, and click on events and training, you'll find a form for submitting an abstract, and that would be now for 2024, since we have all of the 2023 town halls and Dig Deepers filled. Also, there are still some opportunities for sponsoring these Dig Deepers and town halls. Just go to that same location and scroll down, and you'll find a link to the advertising opportunities. Wanted to give you an update on our conference. The annual conference is in December. We're partnering again with NGWA. It's December 5th through the 7th in Las Vegas. We have everything online. If you go to igspa.org, you can register, you can exhibit. There's sponsorship and opportunity and advertising opportunities. They are filling up quickly, so check that out as soon as you can. You can see here we have a lot of sponsors already. We certainly appreciate our sponsors. We do have one gold sponsor left, 3 bronze sponsors, 2 silver, and a diamond sponsor left. So if you're interested in sponsoring, go to that same location and you'll find information about all the benefits of sponsoring the annual conference. Same with exhibitor space. You can see here about a third of that space is already taken up. And if you look at the entrance here on the to the right of the geothermal pavilion, this is one of the main entrances right here. So people have the option of coming through here directly into the IGSPA space or going forward into the NGWA space. So really, any place along this aisle here or on the main aisle between NGWA and IGSPA are great locations if you're interested in exhibiting at the conference. Program guide advertising is available for quarter, half, and full page ads, plus inside cover, and the back cover has not been spoken for yet. So this would be the program that gets handed out at the conference, and it gives you an opportunity to get in front of attendees at that conference. Presenters, we're almost ready to wrap up the abstract submissions at the end of this month. So next week we'll be closing those abstracts. And if you're interested in speaking at the conference, just go to igspa.org, scroll down on that page, and you'll find a link to the abstract submission. You can choose which track you're interested in, or you can suggest a new idea for a track. This year, we're looking at changing that up just a little bit, so we won't just have the 3 tracks we had previously, but we'll be able to have some additional topics as needed. And we'll be making some decisions on speakers late in June. If you haven't muted your microphone, please do so, just to make sure that others can hear the presentation. Some exciting news about the next research conference. IGSPA is partnering with Polytechnique Montreal, and our next research conference is going to be May 28th through the 30th in Montreal at Polytechnique's location. So watch for more news there. You can go to the IGSPA website, and under the conferences menu, you'll find 2 choices, one for the annual conference and one for the research conference. As far as CEUs and renewals, you do get credit for this Dig Deeper. Just make sure in the chat that you include your email and your name, and we'll record those as part of your certification CEU requirements. Just a little bit of housekeeping. If you would, please type your questions in the chat. That way our speaker can complete that presentation. And at the end of the presentation, if there's still time, I will read the questions and we'll get those answered. If we don't get to all of the questions, we'll keep track of it and reach out after the conference. Also note that we are recording this presentation. So if you check back in a couple of days, probably the first part of next week, in fact, you'll find this recording. Just look at the top of the IGSPA main website page. On the home page, you'll find a YouTube icon at the very top. If you click on that, then you'll see the recording for this session. Just as a reminder, again, please mute your microphone unless you're speaking, and we'll be excited to hear from our presenter. Just a disclaimer and potential conflict of interest that I do need to read to make sure that everybody is on the same page here. The upcoming presentation represents the opinion of the presenter and does not represent any official position, opinion, or endorsement of any products or services by IGSPA or its members. IGSPA town halls and Dig Deeper webinars are for member updates and education on the latest information in the geothermal heat pump industry and are not meant to endorse one technology or brand over another. It is the presenter's responsibility to disclose any conflict of interest or position that may arise in the content of the webinar. So with that, I'm happy to turn this presentation over to our speaker, Roshan Revenkar. And again, thank our sponsor, Climate Control Group. Let me introduce our speaker. Roshan, feel free to share your screen at your convenience. Roshan is a professional engineer based out of California with a mission to make ground source energy affordable. He's the Vice President of Marketing at Genesys NZE and is also a member of the Gray Edge Group. He has expertise in geothermal design and modeling and is involved in writing standards and codes for various organizations. Roshan has previously served as the Executive Director at IGSPA, where he developed training and membership programs and also established the organization internationally. He is currently the Vice Chair of ASHRAE's TC 6.8 Geothermal Committee, serves on IATMO's Code Development Task Group, and is a member of IGSPA's Training Committee. Roshan holds a master's degree in mechanical engineering from Oklahoma State University. It's my pleasure to introduce Roshan and turn it over to you. Thank you very much for presenting today.
Thank you very much, Jeff. Just want to make sure my audio is coming through okay.
It is, thank you.
Good morning, everyone. It is a pleasure to be here on a nice Friday morning and presenting to all of you. Thank you very much, the Climate Control Group, for choosing to sponsor this presentation. Truly appreciate it. I have about 30 slides that I would be running through in the next 45 minutes or so, and then we'll leave about 15 minutes for Q&A. I have the opportunity today to present to you CLAD, Closed Loop Advection Device. It is an innovative heat exchanger that is now available in the US market. And you will see some of the neat things that this heat exchanger can do and has the potential to do. We claim it is 50% less expensive, needs much smaller land space, and is more efficient. I have my full name and email there. At the end of the slides, you'll also get to see the email if you need to reach out to me for any additional questions. So it is a Dig Deeper webinar, right? So let's dig deep into what this is all about. Let's talk about the when, where, what, who, how, and why. And let's really dig deep into what is this product all about. Let's start with the why. Why do we need another heat exchanger? There is definitely plenty of heat exchangers available in the market. Why do we need another one? Again, this is all our opinion, and everybody is entitled to their own. We have all been part of this industry for a while. We know there's primarily two categories of heat exchangers: closed loop and open loop. Closed loop has its advantages, of course. It is very resilient. Everything is a closed loop. Pressure is maintained well and is efficient, has thermal capacity. Advantages of open loop also, there's plenty of advantages of open loop. You have a very consistent resource, a lot more efficient than a similar sized closed loop. And many other advantages that come with transferring heat with an open loop. But they both have their drawbacks. Closed loop, you need a lot more land space. In most cases, it may not fly because there is not enough just space to do geo. And there are other disadvantages, a lot more lateral piping and so on. Open loop, of course, there are a few disadvantages which are related to scaling and so on and so forth. You're bringing in an outside resource inside the building or using a heat exchanger, but some of it comes with its own drawbacks. But there's always got to be something better. There's always got to be a different way of doing things. And what I'm presenting in the next few slides is just that. So a little bit of a background of this particular product and the story, when, where, and who. A couple of gentlemen who were in the US in 2008, 2009 had to move back to India for family reasons, but they both worked here for manufacturers of ground source heat pumps. And they learned everything that they needed to about geothermal, 200 feet per ton, closed loop, we're good to go. They decided to move back to India and decide to implement that in India. With 200 feet per ton, they couldn't extract anything in India because the ground temperatures are just too hot and it's all cooling load. So that wouldn't fly. Then they decided to try open loop because that's what they had also learned about. And open loop, they encountered certain issues in that particular region. There was not enough water at times. The water had issues, water quality issues, and so on and so forth. And regulatory issues that they had to battle. So they had to come up with something that would, use both these, the best of both worlds. And that's where CLAD was essentially born, which we will see in the next few slides. Most of the rest of the slides is about what and how. What is CLAD and how is it going to be implemented? Just a very, very basic conceptual diagram of what CLAD is. I'll spend a good couple of minutes on this slide. As you can imagine, it is a closed loop system. We call it closed loop advection device. Typical building with a heat pump, just a schematic here. This could be multiple heat pumps or a pump station where you have two pipes, supply and return, going into the CLAD unit. So a supply and return going into the heat exchanger. Entire looping on this end is closed loop. So similar design criteria to any other closed loop system. The heat transfer happens in a water well. So you do need water, but all of the groundwater remains underground. The heat transfer happens inside the CLAD unit, and we will look at detailed design of this particular device. There is a pump at the bottom of the CLAD unit, a typical water well pump, which is pushing water through the CLAD unit in the opposite direction. So there is a counterflow happening here at the CLAD unit. This water is essentially activating the heat transfer on the closed loop side. It is a double wall heat exchanger, so there is no cross contamination of any sort, which also means that you could use antifreeze on the closed loop side. On the closed loop side, you can design for your typical 2.5 or 3 GPM per ton as you need, and that's what the CLAD unit is meant to hold. On the open loop side, we only need a flow of 0.8 to 1.2 GPM per ton. So nominally 1 GPM per ton, which the way it's designed for much lower yield of what the well can actually produce. There's multiple ways to discharge this open loop side of it. It could go into another recharge well or a discharge well, or it could go into surface water, storm water, lake, or whatever. The flow here is very, very nominal. It's about 1 GPM per ton. We've also designed a cracking pressure device, and I'll talk about that a little bit. And that really helps to maintain pressure even on the open loop side, which essentially means you need very low pumping power for this open loop pump. The neat thing about the way CLAD is designed is all of the open loop piping and all of the water essentially stays below ground level. We've noticed that authorities like that, and that's one of the feature of CLAD, is that all of the groundwater never leaves the ground or never sees the day of light. Now, in reality, this is a little more complicated diagram, but essentially the same concept. You could have a building with multiple heat pumps. Supply return coming from the building, going into a header system, into closed loop or CLAD wells. So if you can think of these are very similar to how a typical closed loop bore field would be designed. But in this case, you only need a lot less number of CLAD wells compared to a typical closed loop system. In reality, you need only 2 to 3 supply wells for every discharge well. We don't need a one-on-one correlation on the supply and discharge. So we talked about, I mentioned briefly this cracking pressure device. This pressure device essentially holds pressure and only opens when there is flow or above a certain pressure limit. What that means is that this particular pump does not have to really do all of the work like a typical open loop pump, where it's got to pump through this entire system into a discharge well. The head really is essentially difference of the water levels between the supply and the return due to this particular device called the cracking pressure device. All of the heat exchange happens inside the CLAD unit. We will look at what material it is made of and so on and so forth. But the CLAD unit can do both what we call active and passive heat transfer. Active heat transfer is essentially when the pump is running, but the material here is stainless steel. All of the heat exchanger is made of stainless steel. So it can also do passive heat transfer, which means that the pump does not need to be running all the time that the unit is, or the system is running. The way we design location of supply and discharge wells are very similar to how you would do in an open loop system, where you pick up the supply and discharge it in the direction of flow of groundwater. And a lot of this information is available online on the direction of flow in general. So pick up water and drop it into a discharge well. Again, it does not have to be discharged into a well. It could go in a surface water or stormwater sewer and so on. Or what we are seeing in a few applications is it's also used for domestic water use if it's permitted there. So this is a schematic drawing of what the CLAD unit actually looks like. I've always shown those rectangular boxes. Now this is an enlarged version of what this box really is. And then the next couple of slides, I'll show what the device looks like as well. There is supply and return coming in from the building. Here is where all of the heat exchange happens. And there is a third pipe, which is the open loop pipe, which goes into a recharge well. What we have at the bottom of this entire CLAD housing is a water well pump. This is nothing proprietary. It's off-the-shelf water well pump from any of the manufacturers that make these. And it's screwed into the CLAD heat exchanger. So essentially, it's just pushing water through the heat exchanger for activating the heat transfer. The entire CLAD assembly is designed in a way that it can be lowered into a well and removed out of the well, just like how you would install a typical water well pump. And this is the neat advantage of one of these, is that if at all this particular pump were to fail, which again on average is about 13 years, all you do is pull the CLAD unit out, unscrew the pump, screw a new one, and drop it back into the same well. Our current product offering is we've got 3 products and another one on its way. We've got 3 models, just to focus your attention on what we call standard efficiencies. We've got a CLAD 6, a CLAD 20, and a CLAD 100. What this essentially means, it's nominal capacity for a 56-degree groundwater temperature is 6 tons. And sometimes I just let that sink sometimes. Yes, 6 tons from one hole. We've got a CLAD 20, which could produce 20 tons from a single hole, and a CLAD 100, which could produce 100 tons from a single hole. Like I said, on the open loop side, it only needs about 1 GPM per ton. So a CLAD 6 would need 6 to 7 GPM on the open loop side. But on the closed loop side, it could have your 18 GPM, which is 3 GPM a ton. We see CLAD 6 as the unit that is going to be used in most small residential systems. Then there is the CLAD 20 and a CLAD 100. And these were specifically picked for the sizes of most geothermal projects that we would be working with. And we have a CLAD 50 on its way as well. And that should be available later this year. On the entering water temperature side, these units are designed to operate between 80 and 43 degrees, 80 on the cooling and 43 on the heating side. We've got two more efficiency models available. These are essentially more number of heat exchangers or more heat exchangers within the heat exchanger body itself. And those could operate in much more tighter temperatures of 70, 45 and so on. Now, this is how the CLAD unit actually looks like. And this is the diagram. It is made of SS316 stainless steel. The finish on the heat exchanger is really, really smooth. It's 0.5 microns smoothness. The reason that was picked was to avoid any growth or fouling. If you can imagine, there will be turbulent flow within these heat exchangers. And with such a smooth finish, there is no growth or microbial growth happening on the heat exchangers itself. It is meant to operate in harsh water conditions and also in conditions where typical heat exchangers would foul. But the advantage of the smooth surface is that fouling is reduced drastically. And like I said at the beginning, the pump could be any off-the-shelf pump. The fittings are designed to accommodate off-the-shelf pumps. Each of these heat exchangers are factory tested. The heat exchangers are proprietary to Genesys. They were designed to fit our ecosystem. But in general, this quality of material and type of heat exchangers have widely been used in other industries in the past. So here is the actual product. This is a 6-ton unit. There's a few videos which I'll just walk through. What you're seeing in the middle is what we call a pitless adapter unit. So this sits on top of the well. This is how you unscrew 3 pipes. So there is a supply and return. And the rest of the connections between the pitless adapter and the CLAD unit is all HDPE pipe, plastic pipe. And this is the actual heat exchanger that sits inside the borehole. Again, the pictures and videos you're seeing here is of a 6-ton unit. Here is an image picture of what we call a well cap unit. So this essentially sits on top of the borehole. Some regulations require you to have at least 12 inches of cap and casing on top of the ground level. And this is what would be on top of each CLAD unit. What this lets you do is it lets you unscrew the whole deal and then pick up the CLAD unit from the bottom up. And this is pretty heavy duty. If some of you have seen this particular unit in our presentations, we exhibited at IXBA and New York Geo and in Illinois. So this was displayed in New York Geo. So this well cap unit essentially has a steel cable that holds the entire assembly that sits inside the well. So the plastic pipe is not really holding the heat exchanger, but it's a steel cable that is holding, which is connected to the well cap unit. A lot of questions have been asked about where will this be applicable. Here's a picture. Here's the map of United States and its aquifers. This is the basic aquifer map. Our focus initially will be in the glaciated aquifers. The blue region shown here is where you find a lot of water, and you can find water at as low as 50 or 60 feet. The questions that we've been asked is how deep are the CLAD units? we only need about 10 feet of water level above the clad unit. So we've got a few projects going on where we have drilled 60 to 65 feet. So each well is essentially 60 to 65 feet. Let me go back a few slides to this particular slide. CLAD 6, in terms of diameter of the borehole, for a 6-ton clad unit, we only need a 5-inch well or a 5-inch casing. For a 20-ton model, we need a 6-inch casing. And for the 100-ton, as you can imagine, there's bigger pipes, bigger flow, we need a 12-inch casing. The 50-ton clad that will be available later this year will need a 10-inch casing. So we're talking essentially 5, 6, 10, and 12-inch for each of these models. We are working with a lot of projects where they currently have water wells, which are either 5 or 6 inches, and clad unit can go right into that and connect to a heat pump if they were to move to a heat pump system. So as a company and as a product, it is a new concept in our market. So we have also designed and developed tools to help design these units. In terms of testing of water availability, again, this is not something that we have come up with. This is just available resources for finding out how much water is in the ground. There are sonar testing, there is drop-down testing, which essentially is you don't have to drill a well, but with these testing tools, you get an idea of roughly where your aquifers are and where your target aquifers are. Of course, for large projects that are 100 tons and above, we recommend doing a one hole and just to get an idea of how much capacity of that well is, so that we can design the rest of the system accordingly. But there are a lot of open source resource tools that are available to give us an idea of how much water is in the ground. For example, if today if we were to receive an address, we can kind of come up with a plan of whether you could go in with a 20-ton clad unit or a 100-ton clad unit and how much water is available in that vicinity. Some of the sales and design tools are what we call a clad sizer. Again, with this being using groundwater, it's a little different than the typical TC tests. You need hydraulic conductivity gradient and its radius of influence. We also need to know what's the capacity of each production and capacity of a diffusion well. A lot of these are geology based, so we need to understand what the geology is, and we have tools to help design these systems. We also have a cost estimator and a proposal builder that is available for use for most engineers. With this estimator, we can estimate the hourly performance of the clad unit and the entire system, and also compare clad with the regular typical closed loop geothermal and other systems that are available out there, just as something that you can put together as a presentation if you were ever to present clad to your customers. Just a screenshot of what the product looks like. It's currently in a very naive state. We are moving this to a cloud-based software here shortly by the end of this year. The CLAD sizer unit is essentially meant for two types of drafts, and the focus here is on the discharge because we know what the supply capacity of the supply is. So what should be the diameter of the discharge well and how deep it should be and so on. Same thing with if we were to discharge into a natural draft sizer, we've got two different sizing tools for each of these aquifer types. The next couple of slides are our test data. We are using propylene glycol, 30% propylene glycol on the closed loop side. So this test data is for the device that you just saw in the last couple of slides. It is a 6-ton unit. In terms of capacity, it produces 6 tons pretty consistently. This test was done for about an hour, just to give you an idea of what the temperatures are. Like I said, 6 tons nominal capacity for 56-degree groundwater temperature. In cooling mode, it enters at 56 degrees and leaves the heat exchanger at 72 degrees, a little less than 70 degrees here in this case. And on the closed loop side, this is what your heat pump is going to see. It supplies temperatures close to 90, coming from the heat pump, going into the CLAD, and it goes back to the heat pump at 73 degrees. One of the things you will observe is the approach temperatures between the open loop and the closed loop side is very, very small. In fact, it's minuscule. One of the reasons being the way the heat exchangers are designed, and secondly, the fact that it is stainless steel material. So this is for cooling mode. For heating mode, the 6-ton unit could produce 3.5 tons of heat of rejection. So you add another ton on the compressor side. So nominally 4.5 to 5 tons for the 6-ton CLAD unit. Again, in this case, it's flipped because it is in heating mode. The groundwater, in this case, is 56 degrees. It drops down to about 48 degrees. And on the closed loop side, we supply temperatures of 30 to 33 degrees coming from the heat pump going into the CLAD. When it leaves CLAD, it is at 45 degrees. So a significant amount of temperature delta happening here at the CLAD unit itself. So your heat pump in heating mode will see a nice 45 degrees entering water temperature for this capacity from a 6-ton unit. Again, the approach or the difference between the counterflow sides of temperatures is very, very small. Here is a project that we are wrapping up in Michigan. On the left-hand side is to give you an idea of the cost that the client had to pay for if they were to do typical closed loop boreholes. It's a 150-ton project. Nominally, they were the design required 72 boreholes at about 400 feet on average. The price they received, or the quote they received, was $800,000. With CLAD, what you can see here on the right, we are going in with 10 20-ton CLAD units. We have an additional 2 just for extra capacity. So a total of 10 CLAD wells at 60 feet deep. So compare that to 400 feet deep and drilling 72 boreholes on site and tearing up the whole lot or the whole play area. In this case, we are going around here. For this particular project, we had 2 options of discharge. One is we could discharge into this lake, and another option was to discharge into discharge wells. Obviously, it was cheaper to discharge into the lake, so that's what we are doing. In terms of permit, we got permits for both to discharge into the lake and into the well. It was just an economical decision to discharge into the lake. All of this project on the groundwork side is being completed and cost the client little less than $400,000. Another project that we are working on, several over 100 wells, boreholes drilled here, replaced with about 16 CLAD units, and these are all 20-ton CLAD units for a facility of this size. One other application that has come our way is what we call bore field rescue. We came across a pretty critical project which had 8 boreholes on each circuit, and which currently has 8 boreholes on each circuit and 8 circuits. So total of 64 boreholes, and they noticed that there were leaks in the circuit. They couldn't figure out where it was. They had to isolate the entire circuit. They suspect there is another leak in another circuit, and they might have to isolate that as well. They've been seeing groundwater, their borehole entering water temperatures creep up in the high 90s and even has surpassed 100. But it's a facility that's already up and running and sees high traffic. They don't want to be drilling another 8 boreholes or 16 boreholes and approached us for a solution. We are going in with 2 CLAD units, so essentially drilling 2 boreholes. And all we are doing is connecting. So this is going to be the production well. This is going to be the discharge well. Production well just connects right into the circuit that was non-operational and discontinued. So the rest of the system stays the same with balancing of flow. The entire system is now going to be up and running with less than 90-degree entering water temperature on the heat pump side. So essentially, if you can think of this as down the whole assembly, repairable, scalable, if there is groundwater available, which in this case there is. An interesting application that we have developed is what we call the CLAD cannon systems. So the entire assembly does not always need to go inside a borehole. If there is surface water available, this entire CLAD assembly is on wheels that is just rolled down into a lake or a well, into a lake or a surface water body. Same 3 pipe connections to supply and return going into the heat pump side, and then a discharge, which of course in this case can just be discharged back into the lake. So this is an interesting applications. We've got all these 3 sizes available in a CLAD cannon system as well. So if there is a surface water body available deep enough to take care of the heating season, then you could just roll CLAD into a lake or a river body, and you're good to go. So with that, just to summarize CLAD, the building loop side still stays as closed loop. All of the heat transfer and heat exchange happens inside the borehole. Use of glycol is possible because it is still closed loop, but uses a well and open loop on the heat exchange side. The closed loop side lets you use glycol because it's a double tube essentially heat exchanger doing the heat transfer. As you can imagine, there is one hole that gives you 6 tons, 20 tons, and 100 tons. So a lot more efficient than a closed loop with a lot less ground area and work needed on site. With the way we've sized these CLAD units into 6, 20, and 100 tons, it is very, very scalable. So if there is a building that needs more capacity, or the use of the building has changed over time, we can always go in with more CLAD units and with very little disruption connected to the existing system. One of the advantages, and this really depends how you look at it, just like an open loop system, there is no thermal buildup, so there is no long-term temperature creeps either on the heating or cooling side. Of course, this also means that it's not a thermal battery. Essentially, it's just a resource or a continuous resource of 56 degree, 52 degree, whatever groundwater temperature available year round. So there is going to be no thermal buildup around the CLAD unit. One of the neat things about CLAD is the entire assembly can be pulled out of the CLAD of the borehole and replaced if there is if the pump fails. So there is no need to abandon wells if there were any underground leakages. This might be the first ground source product that can actually be installed in the ground and taken out of the ground. That seems to attract some of the finance folks as seeing this as an asset now that can be installed and removed from the ground, unlike typical closed loop systems, which once it's in the ground and grouted, it just stays there. In terms of product readiness, the product is currently being assembled. There's few parts and pieces that we are building here, or the critical parts are being built here in the US and currently being assembled in India and shipped back here. So our lead times are about 8 weeks, but it is ready for orders. In terms of component reliability, all of the heat exchangers, as I mentioned earlier, are going to be field tested because they are all tested for such critical applications, make sure there's no leaks and all of that good stuff. And to help design, these are all standardized design and design sizing tools that we have already built to size them for your projects. So having said that, Jeff, I think I'm ready to take some questions. I know the topic is dig deeper, but honestly, with CLAD, we may not have to drill as deep in this case. So Jeff, over to you. Happy to take some questions here.
Thank you so much, Roshan. Very interesting presentation. I appreciate the detail there. And we have a lot of questions. So we'll start with Elizabeth. This was towards the beginning of your presentation. She asks how the 200 feet per ton was determined. Was a thermal conductivity test done? I think that was in your reference to applications in India.
So again, it was based on what we hate to call rules of thumb here in the US. I see Gerald McLean here on the call as well. For most of the people who are on this call know where the 200 feet per ton came. It was from one small solar building at Oklahoma State campus where it so happened to be 200 feet per ton. And unfortunately, that became the industry norm of 200 feet per ton, which I know a lot of people on this call are trying to still deal with that. So that was just something that the guys picked up 15 years ago, that 200 feet per ton would have been the norm. But it is not the norm. Do not design your systems assuming it's 200 feet per ton.
Don't design it that way. Okay, very good. All right, the next question, I believe you've already answered. How many different sizes are available? That's 6, 20, and 100. Is that correct?
Yes, and there is a 50 on its way, which will be available by the end of this year also. So 6, 20, 50, and 100.
Great. Mike asked a question. Are any depth limitations on installing CLAD?
No. So the only limitation in this case, well, not a limitation, it would be more of a sizing component, is that the pump should be able to pump the water at that level, but no depth limitations at all. In fact, we just, as long as the entire CLAD assembly is sitting in water, we're good to go. So in some cases, it would be a 50 feet well. In some cases, it could be 150 or a 200 feet well. I don't see the need to go any deeper than that, unless there is absolutely no water and you want to hit an aquifer that is really, really deep. But which in that case, also it's possible because you're essentially just using a water well to do the heat exchange.
Excellent. Mike asks, if closed loop system is below the frost line and enters the building, why is propylene glycol needed? Steve responded in the chat, you're correct. It would not have to be. It's up to the engineer to decide if they need glycol. Of course, the system will work even better with just water inhibitors. Any comment on that, Roshan?
Absolutely. I think Steve hit the nail on its head. The idea of designing or the design just so happens to be that we can use propylene glycol. It's not something that you would need to, as long as it's all below the frost line. It's more of a liability, and engineers like to add propylene glycol to the system. So in this case, you can add, it's not always needed. Again, if you think about it, the way we've sized these are with propylene glycol. So without propylene glycol, like most of us will understand, the capacities are going to be even better.
Very good. All right, David has a question about the heat of rejection capacity of the 6-ton unit. If the heat of extraction is 3.5 tons, can it provide the 7-ton plus needed for 6-ton cooling load? So
6-ton is nominal in cooling mode for a 56-degree groundwater temperature. As you can imagine, you have a lot more delta to play around with on the cooling mode. So that's why its capacity is greater. On the heat of rejection, on the heating side, is you don't want the water to go below 40 degrees. So very little room to play on the heating side. So that's why the capacity is a little lower. But again, if your groundwater itself was, say, 60 degrees or 65 degrees, you're going to get great heating mode. But if your groundwater really is 65 degrees, your building may not be needing as much heating. So it's really playing around with temperatures and what ranges of temperatures you're playing with.
I think David was asking if it's 6 tons of cooling capacity, it might be rejecting 7 or 7.5 tons of.
Correct. Yeah.
So 6 tons includes
but nominally
rejection.
Yeah, correct.
Okay. Thank you. Terry asks about this comparison to standing column. He said it looks like a standing column system, but doing the heat exchange within the wells without having an intermediate heat exchanger in the building. Do you normally engage a local hydrogeologist for source and reinjection well design to accommodate the CLAD system requirements? Another question, are there water well design considerations to allow for maintenance of the CLAD hardware?
So the first part of the question, we have not had the need to engage a hydrogeologist on the size of projects that we are dealt with. We've dealt with less than 300-ton size projects overall. But I would imagine if you are doing 1,000 tons or more, or a bigger district system, you would need to involve some level of hydrogeologist specialist in those kind of projects. And the second question in terms of maintenance, it's kind of neat. Again, reiterating the fact that the entire system can be lifted up. If there is any scaling on the housing or casing, the way this would be done is you pick it up just like a water well, pressure wash it, and put it back into the existing well. The
Thank you.
bottom of the clad unit would not sit at the bottom of the well. It would be about 5 feet from the bottom of the well. Just to protect the bottom of it, and make sure the pump has enough flow around it to push the water through the clad unit.
Okay, thank you, Roshan. Elizabeth asks the question, what quality control measures are required for the installation? Is there a functional performance test after install before use?
So good question. In terms of quality control for this would be no different than how you would pressure test a closed loop system. So similar testing on the closed loop side. On the open loop side, yes, you would need to know the discharge and the drawdowns of the well, which most drillers know. Like for example, in the project that I showed, the wells were spaced, and maybe this answers one of the questions. What's the spacing between the wells? We've spaced them about 30 feet from each other, the production wells. And there were tests done where to check the water level on the second and the third well. If you were drawing a lot of water, does the first well drop its level? So those kind of drawdown tests would be needed on large projects, but that can be done on site while the drillers are on site. So that's what happened in our case. For a 150-ton project, the drillers were there for 1.5 weeks to drill these 10 wells, put their casing, and they were gone. So just very little time on site. When we will install these clad units, you will see that the testing would be very similar to a typical closed loop system.
Okay, thank you, Roshan. John asks you to discuss typical maintenance and potential life cycle maintenance costs with the pump.
So a typical life cycle for these pumps are 13 to 15 years just for the pump itself. So in that case, every maybe 10 to 15 years, you pull out the whole unit and then unscrew the pump, put the same pump back in, and drop it into the well. The rest of the material, it's all stainless steel. So again, there's no answer as such. Just like how closed loop, we've always been asked how long can closed loop last, right? And the answer is what, 50 years, 100 years. It's stainless steel. I think 30 years would be a good number to have on your legal paperwork. I'm sure it's going to last a lot longer.
Okay. And Lance asks, what type of pressure testing and quality controls performed on each clad unit in the manufacturing process? Are they produced and or tested in accordance with any industry standard?
Yes. So similar pressure testing standards as the closed loop systems on the closed loop side.
Okay, this is at the manufacturing testing, I think he's asking.
Correct.
Okay, all right. Elizabeth asks, how is vertical piping removed to replace a clad unit or component of the unit?
How is the vertical piping removed? Is that the
Yes.
question? So this would be
replaced.
very similar to installing a water well pump. The way we've designed CLAD is it's just an extension of, if you can think of a water well pump, which is essentially this little pump here that is dropped with the piping. Instead of just the piping above it, now you have a heat exchanger and 3 pipes. At the top of the well, I know it's kind of hard to see, we use the same pitless adapters that are used by the water well industry. Instead of using one pitless adapter, we have them in at 120 degrees from each other. So these are 3 pitless adapters. So the entire assembly can just be pulled out of the system. The pitless adapter unit is sized so that the entire clad assembly can be pulled out along with the pump, and then so you probably need some place to hook it up. There is an eye bolt at the top, so you essentially just lift the whole deal up.
Okay, great. Presentation is drawing a lot of questions, so we still have quite a few more here. Bob says there may be no thermal buildup at the point of installation, but there will be downstream thermal plume that might impact neighboring installations. Any comments on that?
Well, if we are ever in that situation, we would love to be in that situation, right? Like in Sweden, where you have so many closed boreholes next to each other. But on thermal buildup side, the groundwater has a lot more capacity than we can imagine. So even if there were lots right next to each other, you could place them strategically around the building in a way that the direction of flow takes the heat away with it. So yeah, I guess I hope that answers the question.
Okay.
But in terms of groundwater capacity, I get asked how much can each well produce. So if you can think about it in good sources areas, these wells have the capacity to produce 300, 400, 500 GPM. It's a lot of groundwater. And we're just adding very, very little heat to it, or drawing very, very little heat out of what it can actually produce.
Very good. All right, Andy asks, are there any limitations on pump setting depth? We work with aquifers that could be running with 200 to 300 feet pumping water level. And so manometric head would be in excess of this. Also, how does the crack discharge valve mitigate the drawdown in the abstraction well?
So if you can think of it, the actual pressure is the difference of pressure between the water levels. So think of it as a siphon effect. That is what is created by this cracking pressure device. So the actual pumping power on the pump at the bottom of CLAD unit is much lower. And again, these are variable speed pumps, so they will run at low speeds if that's what you need. These are CLAD is always designed for peak capacity. So your heat pump may not be running at peak all the time, as we all know. So the pump also will be running at very low speeds. And with this cracking pressure device, it doesn't have to be running at full speed to generate that kind of flow.
Okay. Victor asks, what's the oldest installed application? How stable is performance over time? Have you seen cases where water level drops, wells dry up over time? If so, how do you design to avoid this?
So there are no old enough applications in the US. Genesys was launched at the IXPA show last year. So we have few installations that are being wrapped up this summer. In terms of the oldest applications of CLAD, of course, overseas in the Middle East and in India, these have been installed for about little over 6 years now, with no issues that have been reported.
Okay. See, Pete asks about retrofits available and surface water requirements.
So I'm assuming the question is, can these be used for retrofits?
I believe so.
Okay. Yeah, absolutely. Because if both for retrofits and existing water wells, if there is an existing water well that just has a pump and all it's doing is pumping water out of the ground for domestic water use, instead of just doing that, you could install CLAD and have the same pump at the bottom of it, or maybe a different pump in this case, and can be used for existing applications that have wells, or you probably need to drill more wells. And on the groundwater piping side, if you can imagine, you don't have several boreholes that need to be connected, so the trenching work is going to be much less. So fits really well for retrofit applications. We are looking to finish up a hot water heating project on, right close to Central Park in New York, and very little space there. But all they will do is have 3 CLAD units on one side and 1 discharge on the other side of the building. It is a retrofit application. So yeah, as long as you can locate the production well close to where the mechanical room is, to avoid minimum piping and disruption, it seems like a very good option to use CLAD.
We have about 3 more minutes. We'll get to as many questions as we can. Gino asks about insertion in a pond or lake.
I love that, because this has drawn so much attention into a pond or lake. The way this would be done is all of the piping will be completed, and it's essentially rolled into a pond or a lake, and then somehow it's stabilized again, with pond and lake applications, as some of you might know, you don't necessarily have to be at the bottom of the pond or lake. It could be along the slope to have, because the water tends to move between layers within a lake. So this could fit somewhere there. And then the discharge could be in the lake, just at another location. To be very honest, we haven't installed one of these, but after the 2 conferences, I'm pretty sure we'll have one up and running by the end of this year, if not earlier.
Okay, very, very interesting. Roger asks, in the injection discharge well, is the cracking pressure adjustable for ensuring no error into the CLAD system, depending upon static water level? What diameter sizes are available?
So great question about air in the system. If you've heard of iron bacteria, that's where the problem occurs, is if there's air in the system. The way the cracking pressure device is designed is to maintain pressure and no air on the open loop side as well. So the cracking pressure device essentially only opens when there is enough pressure coming in from the pump discharging water into it. So there is going to be no air in the system.
Okay, very good. Elizabeth is asking if there's a functional performance of the heat exchange, maybe relating to the software.
I'm not sure I follow the question, but if it is related to design of the heat exchange, yeah, these are designed for peak loads essentially.
Okay.
And then again, one of the questions we do get asked is, well, you are adding a pump to the system, so there is going to be more energy use, right? If you think about it, a lot of the heat pumps like to operate in the temperature that CLAD is providing, which means that the heat pumps are operating at much better efficiencies. Yes, there is a pumping involved. I talked about active and passive heat transfer. So the pump is really running only when there is active heat transfer happening. So the pump, in the whole scheme of things, would run only 30 to 40% of the time. And these pumps, if some of you know, they use very, very little power to operate. And the energy used by the pump, or the energy savings from the heat pump side, definitely offsets the energy used by the pump. So overall, the efficiency of the system is the same or even better.
Okay, very good. Well, I wish we had more time, but it is right at 11:30 Central. I will keep track of all the questions we didn't get to and send those to Roshan, and we'll get back with you. Thank you so much, Roshan, for presenting at our Dig Deeper, and thank you everyone who attended. It's always great to get this interaction, and we will continue to do more and more of these Town Hall and Dig Deeper webinars. Have a great weekend, and stay tuned for the latest news from IGSPA. Thanks a lot. Bye.
Thank you very much. Bye.